Good day. Welcome to the fifth lecture in Calculus 1. So, let's begin. Alright, so for this lecture, we will discuss area under the curve. So, in the previous lecture, I already introduced to you the application of definite integral. So, if we have this kind of expression, so the interpretation of this is simply the area under the curve bounded by x equal to a and x equal to b. So the curve here is what we call f, or f of x. So to have a picture of this, so I will draw a Cartesian plane, and then we have this function f. So this is f, and we bound this f between two vertical lines. So we call this first vertical line x equal to a, and for the second vertical line we have x equal to b. So in order for us to compute the yellow area, we need to find the definite integral of f from a to b. What about if we have a function looks like this, and that function, so we call this g, we bound this g by using two horizontal lines. We call this y equal to c and y equals d. So we need to get this yellow area. So to do that, so the yellow area is equal to the definite integral from d to c of g of y, so dy. So this is how you compute the definite integral of g if you have this kind of figure. Alright, so for example, we have f of x be x squared. So where x is bounded by the number 0 to, let's say, 2. So here's the graph of the function. So this is f. So we bound this f from 0 to 2. So this is x equal to 0 and x equal to 2. So that means this value here would be 4. Now, first thing we need to compute is this green area. So to do that, so the green area can be computed by getting the definite integral from 0 to 2 of the function x squared dx. So we all know that the definite integral of this simply, so we evaluate this. So we have x cubed over 3, so evaluated from 0 to 2, so we have 8 over 3. Now, what about if we have this orange, yellow area? So the yellow area can be computed by getting the integral from 0 to 4 of the function square root of y dy. So if we evaluate this, you will get y raised to 3 over 2 all over 3 over 2. So evaluated from 0 to 4. So that gives you 16 over 3. Alright, so as we can see, the yellow area is not equal to the green area. Alright, so let's talk about volume. So we already know that in order for us to get this function, let's have this. So we call this f of x equal to, let's say, x squared. For example, if we bound this function so this is from x equal to 0 to x equal to 1, and then we take or we revolve this function about the x-axis. So this is x, this is y. So you will get this kind of figure. So it looks like this. So we shade this. So imagine that this is kind of a cone, and we need to get the volume of this kind of solid. So this looks like this. So this is a solid figure. Yeah. So in order for us to get this kind of volume, so we will slice this this solid And as we can see, we will obtain a circle here, and then we look for the area of this green circle. So we all know that the area of the circle this is a circle, is equal to pi r squared. So our r in this figure would be the function x squared. So we have f of x, which is x squared. So by that, so the red volume is equal to, we integrate the area r squared. So r is x squared, so we have to square this. So dx, so from 0 to 1, which is equal to pi integral from 0 to 1 of x to the 4th dx, which is equal to pi over 5. So the volume of this figure, so volume equals pi over